So this is IIT Hyderabad. CSC.
Wow.
That's a big. Where is your office?
So slide the click करके एक बार click करते हैं.
This one. Okay, I'll point there.
Can you just move that thing? Just minimize the thing. Yeah. What?
Why? Why would you not let me? Okay, welcome again. I'm very happy to introduce Rameshwar coming to us from IIT Hyderabad. He works in algorithms for massive data sets, specifically sampling and dimensional reduction. And he tell us about efficient indexing for locally sensitive hash rate.
Just click on this slide one. I think.
We have a click, right?
Thank you, Raghuvansh, for inviting me. So to begin with, I'll just show some pics from my institute. So this is our CSE department. We shifted here in last month. And what do you think this is?
Library.
Library. This is our library. And any guess what is this building?
Student activities.
Huh?
Student Activity Center. SAC.
So this is library only from outside.
Question.
Good question. And what do you think, Ramprasad? You can add.
Hostel.
Computer science building from the other side.
No. So this is our guest house.
No.
So I'll take this opportunity to thank you for invitation and please visit our department sometime. I'm happy to host you.
Is there a diving board?
Huh? Sorry. So this is artificial pond or lake. What?
The guy was a driving board.
Okay, so this is outline of talk. So first I'll talk about nearest neighbor search, and then we'll see locality sensitive hashing algorithm for nearest neighbor search. Then we'll see algorithm E2LSH, which is LSH for Euclidean distance. So until this part, I'll be mostly overviewing the LSH framework and LSH algorithm for Euclidean distance. Then we'll see our contribution, which is faster and space efficient. Faster and space efficient indexing for locality sensitive hashing, which is joint work with my PhD student, Vishnu Verma, and it got accepted in TCS Journal. And basically in our contribution, we are proposing two improvement of E2LSH, one using count sketch, another using higher order count sketch, and then we'll see experiments. So in nearest neighbor search problem, we have given a set of endpoints in RD, P1 to Pn, and we have given a query point. And our aim is to find nearest neighbor of Q from the given point in our data set. So if we want to solve this problem exactly, there are kind of two extreme approach. One is using full indexing, using Voronoi diagram kind of algorithm. For that, we get faster query time. It's logarithmic in number of data points. But in terms of space complexity, it is exponential in dimension. And the other extreme approach is linear scanning. For that, both query time and space complexity is ordered in. So basically, the first approach becomes infeasible for largely, that's we call skulls of dimensionality. So now, instead of solving the problem exactly, we'll try to solve problem approximately. So instead of finding exact nearest neighbor, we'll try to find a good approximation of nearest neighbor. So the problem setting is, we have given a set of endpoints P1 to Pn in RD offline, and we have given accuracy parameter epsilon. And by offline and meet, we can arrange these points the way we want. And once we have query point, we need to output the closest point to Q in kind of quick time. So once we have given a query point Q, we need to find an object Z that is more similar to Q, such that distance of any point from P to Q, if the distance of any point from P to Q is say this much, then algorithm can report any point Z whose distance is not more than 1 plus epsilon times to the original distance. And if it is true for any point, so it should also be true for the point which is closest to Q, right? So we'll see that this approximate similarity search can be done in sublinear time. So now let's first focus on easier version of the problem, which we call it as approximate near neighbor search. So here we have given our input is a set of endpoints P1 to Pn in RD, and we have given one accuracy parameter epsilon and one distance threshold R. These two are given to us in offline manner, and we have given one query object Q, and our aim is to find an object Z that is most similar to Q, such that if there is any object Y within distance radius R from Q, then algorithm can return any point P within distance 1 plus epsilon times 2R, right? And if there is no object in our data set such that its distance from within distance 1 plus epsilon times R, 1 plus epsilon times R, then we just say no. Right? So let's see this with an example. So this is suppose our data set, and this is our query point. And suppose there is some point within radius R from Q, so there is one point Y, then our algorithm can return any point within radius 1 plus epsilon times R. Right? Algorithm can output either this point, this point, this point, or any of these points.
Who has specified R?
R is parameter given to us. Right?
So R is R coming in every query, or is R is something that's fixed?
R will decide. So just wait for next slide.
Sure. Okay.
And in this case, there is no point within radius 1 plus within radius R. So algorithm will output no.
I mean, the algorithm should output no only if there is nothing in 1 plus epsilon times R.
Yes.
Okay.
R is part of algorithm, like it's parameter given to us.
No, only in R, right?
Huh?
Even
There
if,
could be a point in the 1 plus epsilon.
even if it's in
So
the.
if there is any point in this perimeter, then there is no guarantee.
Yeah, it could output it. That as well. I mean, the previous slide, the thing just said that if the query point has nothing even within the radius of 1 plus epsilon times R, the algorithm is expected to say no.
No, I think.
Can you
Soft-
please show the previous?
Okay.
In between R.
Yeah.
So if there is no object within radius 1 plus epsilon times R, then algorithm will return no.
So there's something only in the annular region, then you can do whatever you want.
Right. So then there is no guarantee.
So why do you need this? Like, if you don't, like, if there is no point in R, then you can return.
So this is how basically this is problem statement, and LSH will solve this problem statement.
My question is, why is the second condition? Like, when there is no point in 1 plus epsilon R, like, can you get rid of the epsilon there? Like, will it be equivalent to solving it exactly?
Yes. If you get rid of epsilon, then the problem will.
No, for the second condition. If there is no point in R, radius R, then return.
So then in particular, you should be able to distinguish between whether there is a point at radius R or
not.
So you can do a binary search kind of a thing.
So then again, we'll back to the like kind of indexing the original
Exactly.
like Voronoi partition kind of thing. Then the time complexity will be exponentially increased.
So, okay, so my understanding was that, the point is when given a query point, and if you manage to design some algorithm that returns an output, which at any point, the only thing you know at this point of whatever you are outputting looks like 1 plus epsilon within 1 plus epsilon times R from the original thing. There is no additional information you are gaining from. This 1 plus epsilon times R could be that either there was a point that was closer, but you still return the farther away. Or maybe there was no point that was closer, but there was something that was slightly further away. Maybe your algorithm can't even tell the two apart.
Yes.
Yeah. I mean, I don't see what would go wrong if you insist on the stronger thing.
Yeah, I imagine.
If you insist on the stronger thing, don't you have to know the exact distance to the nearest point?
Yeah.
Yeah, so
You can do a binary search.
binary search then.
I mean, binary is not a lot because R is.
I mean, R is the offline parameter,
But I think this is kind of standard because I mean, one thing is that you don't want to do like comparisons with real numbers. Okay, in any kind of computing real numbers, you always want to only compare up to.
Yeah. So if we want to do binary search, you end up getting this exponentially.
But I mean, as you've said, you cannot do binary search because
R is a fixed.
Yes.
Presumably.
But still, you have to do the exact computation. Likely.
So Okay, so we'll see that if we can solve approximate near neighbor search problem, then we can solve approximate nearest neighbor. So for that, we need to have some estimate of smallest and largest pairwise distance. Right, so suppose the smallest and largest pairwise distance are phi and psi respectively. Then I can choose R as phi, 1 plus epsilon times phi, 1 plus epsilon square times phi, and so on. And then we need to solve, run this algorithm for approximate nearest neighbor search these many times, like log of phi by psi in base 1 plus epsilon, right? And then we'll report point, which is we found the first time in the smallest radius. That will be n enough. Right? So is the setup clear? So we can choose R based on, here we assume that phi and psi are given to us, and we can choose R like this. Right?
But this again done sort of in an offline.
Yes, this is done in offline.
So you run these several data structures.
Yes. And tool for solving this approximate near neighbor is a well-known algorithm, which is called locality sensitive hashing. So locality sensitive hashing, it's basically a hash function that maps points into buckets such that similar points map into similar bucket, same bucket, and dissimilar points map into different bucket with high probability. So it's kind of hash function. So we input is our points and it outputs some code like hash value, which is you can think of ID corresponding to these buckets. Okay? And this hash function gives the guarantee that if points, their distance is small, with high probability they'll map into the same. So the advantage is we need to only care about the points which are in the same bucket. We don't need to worry about all the points. And the disadvantage is there could be some false negatives. So points which are not similar, but by bad luck they map into the same bucket. Right?
The property is with respect to the hashing seed, I presume.
Yes. So locality sensitive hashing. So I'll now define locality sensitive hashing mapping. So locality sensitive hashing, suppose X is data set and distance is some distance space. So a family of hash functions like R, a family H is called R1, R2, P1, P2 sensitive hash family. If we take any pair of points from the data set, probability that their hash value is same, h of p is equal to h of q, is at least p1 if distance from p to q is at most r1. So basically, if the points are close by, then probability that their hash value is same is large, right? So you can think of, and if the distance from p to q is at least r2, then probability that their hash value is same is at most p2. So you can think of p1 as say 0.9 and p2 is say 0.1, right? The points are similar with high probability they'll map into the same bucket. So this is framework of locality sensitive hashing. And this is kind of algorithm. So suppose these are your data points. Right? You design some hash functions and using that satisfy the locality sensitive hashing property. And these are different buckets and these points are mapped into these buckets. Right? And once we get query point, we hash using the same hash function and see in which bucket it get mapped. It is suppose it get mapped into this bucket. So now our task is to compare the distance with the points which are present in them. We don't need to worry about very many points, right? And we repeat. So this is for when our hash function gives 1-bit hash code. So what we do to get higher probability confidence, we generate hash function of size k, right? So we just given a hash function h, we just generate h1, h2, hk independent hash functions. So now our hash code is k bit size, right? And each hi is chosen uniformly at random from our hash family, and each hi is a single bit hash code. And then we repeat this entire process L times. So each hash code is of size k, and we are repeating, basically we are generating L buckets, L hash tables. Right? So we generate L hash tables, and in each hash tables we hash all the points. Right? So let's see. So suppose this is corresponding to hash function G1, this is corresponding to hash function G2 and so on, and these are our data points. And using G1, they mapped into these buckets and so on. Right? So we repeat this entire process L times. Right? So now, once we get query points, the query point is mapped into all these buckets. Now so suppose in this case, query point mapped into this bucket. For G2, it mapped into this bucket and so on. So now we take union of all the points present in the same in the same bucket, right? And take union of all of them, and check which has report the point which has the minimum distance to the query, right? So this is
So just want to make sure I understand this picture. So each GI, it has 2 to the K buckets or something.
it
One
can have
has
2 raised to power k bucket.
2 raised to power K buckets, and we are sort of thinking of it as K different, L different hash tables.
Yes.
Uh,
But in practice, we don't generate 2 raised to power k buckets. We generate only if it is required. Right? So suppose you get first point, you compute it hash code, and accordingly.
so this is the range of each GI could potentially be.
Could be 2 raised to power
Okay.
k.
Okay.
All right. Any questions on this? So yeah, so if we use only 1-bit hash function, the probability of sharing a bucket and distance between a point is kind of like this. But for our hash functions, LSH property, to satisfy LSH property, we want this kind of shape, right? Because we want, if the distance is smaller than some threshold, the probability of sharing a bucket is large. And if distance is smaller than certain threshold, distance is larger than certain threshold, the probability of sharing bucket is very small, and the distance is smaller than certain threshold, the probability is large. And that we achieve it by this scale bucketing thing. Like in each hash code, we have k-bit hash code, and we repeat this entire process 8 times. Right? So if we choose K and L properly, then we can tweak this shape the way we want. Right? So if we don't do it, we'll get this straight line kind of thing. If we choose K and L, we can kind of tweak this curve like S shape. Right? So if we use this LSH framework, then we get the following guarantee. The space required to store our data points hash table is superlinear in n, is n raised to power 1 plus rho, and the query time is n raised to power n. So space for storing data points hash table is superlinear, but the query time is linear, where rho is 1 by 1 plus epsilon, it's smaller than 1. So this is general LSH framework. And based on different data type and similarity measure, we can design different hash functions. So now I'll talk about LSH algorithm for Euclidean distance.
How large is typically D?
D could be like in practice few hundred to maybe 1 million and so on. Right? So we'll see some experiments. So LSH for Euclidean distance was proposed by Indek and Motwani. So the algorithm is, suppose these are our data points, and we generate a random line R in D dimension, whose each coordinates are sampled from normal distribution with mean zero and unit variance. Then we project point on this random line, take the projection and shift them by number B. Right? So it is a projecting point on this random line plus shifting them by a random offset B, and then grouping them into a bucket of size W. Right, so hash function for Euclidean distance is this.
What is B doing?
So B is just offsetting. So okay. So first you project point, and these are the projected coordinates. Then you shift them randomly by B. Right? So this is hash function. Inner product of R plus P, R with P plus B by W. And they showed that if we use this hash function, we get the guarantee that is required for LSH. Probability, if we take 2 points P and Q, and such that their distance is R, L2 distance is R, the probability that they will share the same bucket, their hash code is same, is inversely proportional to R. So if distance increases, the probability of collision will decrease. This is what is required. Is this fine? And this proof crucially used the fact that this R is from normal distribution. Each entry of R is follows from normal distribution.
Was B even like why is B needed? The offset in my rules.
So what happens is, if your 2 point source projections are very close to some integer, then they will be, if you don't have B, they will definitely be mapped to different buckets. But if you offset them randomly, there's a probability they will map
I
to-
see.
Is this fine? So now the process of generating k-size hash code can be seen like the following. Suppose this is our input vector. So we generate a projection matrix of size k cross b, whose each entries are from Gaussian distribution. And for b, we generate a random vector b, whose each coordinates are b1 to bk, all sampled from 0 to w. W is some parameter that we fixed beforehand, and b is some random number from 0 to w. So this is just multiplying this input vector with a projection matrix plus adding a random vector. So this entire step can be seen as, and then we finally discretize by W. Right. So in a way, you can think of generating this hash code of input point is random projection followed by discretization. Right. So what is time complexity for this? To generate a k-bit hash code of a data point is order kd. Right. Which could be impractical when k and d are large. Right. So our contribution is to improve this, and this is basically the time required for creating hash table, which we referred as indexing. Right. So time required for creating k-size hash code for a data point is order kd. D-dimensional data point is order kd, and space complexity is order kd because we need to store this projection matrix which has kd entries. It is dense matrix. Is this fine? So our contribution is to improve on this time and space complexity involved in indexing step. Okay, so we suggest two improvements. I'll cover them one by one. So first improvement is using count sketch. So count sketch is another classical dimensionality reduction algorithm proposed by Charikar, and which takes high dimensional real valued vector as input and output low dimensional real valued vector, which preserves pairwise Euclidean distance and to norm and so on. And it also been used in frequency estimation in streaming dataset. So now I'll give you a quick introduction to this count sketch by this example. So suppose this is our input data point, say in 5 dimension, and we want to compress it into 3 dimension. Right? So we generate two hash functions. The first hash function allocate these coordinates to one of these bins uniformly at random. So for example, for each of these coordinate, we generate a random number from 1 to 3. For this, suppose it turns out to be 1. So we link this coordinate with this bin. This is random binning. And also for each coordinate, we generate a sign either +1 or -1, each with probability R. So suppose for this coordinate, we get +1, for this one, we get -1, so on. So our compressed vector is basically we take the value present in each coordinate, multiply in the corresponding sign, and add them up. Right. So for this, for example, for this, this bin will get +2 and +3, 5, and so on. And they showed that the compressed vector preserves pairwise Euclidean distance and inner product if we use the same hash function to compress all the data points. So if we see carefully, this entire compression from P to CSP can be seen as matrix vector multiplication, right? So where this matrix is, so first row of this matrix will be will have non-zero values corresponding to the coordinate which map to first bin, right? So first and third coordinate map to first bin. So first and third coordinate will be non-zero, remaining will be 0, and they will take value corresponding to the value assigned to their corresponding those features, right? So, right? And each column has only one non-zero entries. So number of non-zero entries in this matrix is D, right? So our contribution is
This is a compression thing only.
compress.
I mean that also okay.
So basically, compress input vector and give the guarantee that the compressed vector will preserve or L2 norm and
Yeah,
realize
yeah,
it
yeah.
inner product and so on.
Compress is the opposite.
Opposite,
Yeah.
yeah. From compress, you need to recover
Yeah,
the.
you need
So the solution vector is supposed to be sparse,
Mhm.
then recover it.
So our contribution, so this is kind of crux of the work. So basically, our contribution is to replace this dense projection matrix with sparse count sketch matrix in LSH code generation step. So that so each coordinate this matrix has only d non-zeros. So the time required to multiply this matrix with this input vector is already instead of k. And then we show that then under certain kind of parameter constraint is satisfied, this kind of hash code generation give the same guarantee as of what we get in original E2LSH. Right? Is this fine? Okay, so suppose this is our input point and we compress them using count sketch and the coordinates are CSP1 and so on. Then suppose we want to generate k size hash code. So here we can generate this k size hash code in one shot, like by applying one count sketch matrix of size k cross b. LS bit.
Just to make sure from my understanding, there is no difference between the procedure for compress sensing also is a locality sensitive hash, right?
Sorry?
Is that compress sensing also gives a locality sensitive hash?
Compress sensing
Not
is
the-
different problem and locality sensitive hashing.
So count sketch is different from this.
No, but
To solve for us, if you want to solve for a vector that is sparse, then it's underwritten with very few equations. And you have to solve for that, so it's AX equal to, but the number of variables is very small. Much smaller than the number of variables, but you know the number, very sparse, few of them. Okay, and you have to solve for it.
These two are different problems. Like,
so okay, so can you go back one step? So you do the
so this is for solving approximate nearest neighbor search problem.
okay.
Compressed sensing, like we assume that the input vector is sparse and we have given its compressed version, and we want to recover the original.
Oh, so your CH was count sketch?
CS is count sketch.
On the next, okay, so the same thing I wanted to say the count sketch. Okay, I went the same sentence with count sketch. So count sketch is just one form of locality sensitive.
The count sketch is one way of one dimensional reduction algorithm which preserves L2 norm and inner product and so on.
Okay.
Right? It has not been used for locality sensitive hashing. So this is what we introduce, like, what we propose in this one.
But this is essentially what you show, that if you run
Yes.
the count sketch, it will be locality sensitive.
So basically our contribution is we replace this dense projection matrix with sparse count sketch matrix and rest of the things works.
Okay.
So just want to, so computing this, whatever, the count sketch matrix times the input vector, that matrix vector product. There has to be a faster way of doing that.
NNZ.
It's NNZ of
number of
NNZ of
zero, two, like lots of zero in it. Yeah.
No, but a row could be dense still, right?
No.
All we know is that
Total
a
number.
column has at most one non-zero entry. But a
that's
row
fine,
could
because
still
that's
have
total number is non-zero entry.
So total number of non-zero entries in this matrix is can be D only.
Yeah.
So you store it like that.
Oh, I
Or
see.
other way of
Oh,
looking at,
sorry.
like you are using this count sketch matrix like this. Like you are touching each index only once.
Yeah,
Right? So
okay.
the running time will be NNZ of P, not D, but I'm writing it as D only. The number of non-zero entries will be the running time of applying count sketch. Okay, so basically, suppose P is our input vector and CSP is the corresponding compressed vector in K dimension. And suppose we want to generate K size hash code of a given data point. So the Lth coordinate of hash function will be this root K CSPL plus B by L. This root K is basically just some scaling that happens in JL versus count sketch, pairwise system. Right, so hash function also exactly same. But we need to show that so the comparison with state of the art E2LSH gives time and space complexity order KD, AC hash proposed by Das Gupta et al. They give, it's for indexing time, they give time complexity d log d plus k. Ours improves both of them by time complexity order d and space complexity order. So now we need to show that this, we call our algorithm as CS E2LSH. We need to show that it is valid LSH. To show that, we need to show the following two things. Each coordinate of this CSP1 to CSPK follows normal distribution and they are independent. Because they have been crucially used in the proof of E2LSH guarantee. And we show that using a variant of central limit theorem, right? So we showed that if P is our input point, then expected value of mod of P raised to power 2 plus j is finite, and K is small of d, then lth bit of count sketch.
So P is random.
So P is input point given to us.
What's the expectation of?
So we are assuming that like this moment of point is input point is finite. So roughly it means that entries of our data points are not very large
But
The
what is the
expectation is over the coordinates.
over the coordinates.
over the no, but it's for every j. Oh, so it's over the points.
Over
Over the points.
the coordinates. So j is some j
But
is
it's for
index.
every j in T,
For j-
the
so this is-
delta moment of the j coordinate.
So basically each we are roughly saying that coordinates are not very large of our data.
So precisely, another criteria will be that the sum over all the points of the jth coordinate raised to power 2 plus delta divided by the number of points is small. It's fine.
Something like that.
Something like that. Yes.
Over all the
It's not
points.
growing. It's
Yes.
not growing.
The
Or
j
is it-
coordinate of all the points.
So
J
that,
coordinate.
if I look at the first coordinate of all the points, they
points.
all look roughly,
Mhm.
none of them blows up.
They are not close.
Okay.
And so basically each coordinate is not very large and k is small of d. Then this the what we want holds, like the lth coordinate of CSP follows normal distribution. And to show this, we need to show also we need to show that this CSP follows multivariate normal distribution. So basically we want to show these two things. CSP1 to CSPK follows normal distribution and they are independent. So we show it by following two things. First, we show that each of them are follows normal distribution. Then we show that this entire vector follows multivariate normal distribution, and then we show that each entries are independent. Right? So this is what we show
And this convergence distribution is as the number of points goes to infinity.
as d tends to infinity.
Or as
D
the
tends to infinity.
yeah, number of dimensions.
As dimension tends to infinity, then this goes. Okay. So using a variant of central limit theorem, we showed this. And then we showed that for multivariate, that CSP, that k-dimensional vector follows multivariate normal distribution under similar condition, like expected value of pj is to power 2 plus delta is finite, and k is small of delta by d 2 plus 2 delta for some delta greater than 0. You can think of like delta is 7, just to understand this thing. So basically, roughly each coordinates are not very large, and k is small of maybe 1 by 6, d raised to power 1 by 6. And then we show that each coordinates are independent. If these two things hold.
I have some confusion about the independence part. So we know that in all the k coordinates, the parts that are summed, the entries that are summed, they are disjoint, and then so it forms a
Yes.
population, right? So if let's say you have a vector such that only one of the entries is, let's say, like root 2 is some irrational number, everything else is rational. Then you know that only one of them can be irrational.
But then it will not satisfy this property.
No, it's some small irrational number.
Okay.
Everything else is rational. Let's say it's root 2, everything else is 1 or 2.
Mhm.
Now you know that only one of the sums can ever be rational, one will definitely be rational. So
Okay.
how can they be independent? You know that something is irrational, you know the other thing is not irrational.
We did not get you.
So you have a vector,
Yes.
one of the coordinates is √2,
Hmm.
the others have 1 or 2,
Hmm.
okay? You do your count stitch on this,
Yes.
whatever small vector I get,
Hmm.
I have the promise that only one coordinate will be irrational.
Okay.
I think this is also in distribution, like that it converges to a product distribution. Is
Yes,
that-
converges to this
But
multiplication
then,
of-
so actually, why are these two different statements? That one already said it's converges to a product distribution.
And this one says that each
They are
element
actually
is
independent.
independent.
Yeah, but then.
So, okay, so one of the, so we know that in the small vector, only one coordinate is irrational.
Hmm.
Now, that means that the coordinates are by definition not independent. Because if I tell you that this is irrational, you know that the next one is not irrational.
No, independent in the sense that, so, okay.
But to be said that as G tends to infinity, they are different. It's just that they are, basically,
Okay.
they are never different actually, but they get closer and closer to it.
No, I think that's not because
That
that
is not
because that is anyway follows from the first one because it's a converging to a product norm.
But then the second statement was the same thing. Because
Oh, is the second statement the same thing as the first one? Then
No, one second. So suppose this is your input point and you are compressing it using this JL projection matrix. So each coordinate will be independent, right? Because each row is
Each row is independent.
independent.
Yeah.
So we are just replacing this by count sketch.
yeah.
Yeah.
And then we are showing that this each coordinate of this CSP are independent. Under if
Yeah, so that's the thing that the same problem because
it's like this is small and this K is also small. So basically if K is small and each entries are small, then the projected
I
will
have a
follow.
problem even if K is 2 and the thing is finite. So it is, just imagine K is 2. So you have the coordinates go somewhere, half the coordinates go somewhere else. The √2 will only go to one of the locations. So one of the coordinates will always look like some integer plus √2. The other coordinate will always look like some rational plus √2, and the other one will always look like some rational.
That is fine. Then like why √2 has issue with not
because then it's with condition on P, these are not independent.
Because then one coordinate gives you information about another coordinate. So if you didn't know the other coordinate, this one could have been irrational for all you know.
So technically speaking, I mean, like it might, I don't know if it is the case that right now, okay, there was the locality sensitive hash that was previously defined had multiple components, right? There was a point where you take the inner product with a vector and then you translate it and then you discretize it.
Yeah.
Is this a statement saying that post discretization they look independent? Or
So look independent is fine. I mean that is already said by the first. They're sort of close to being independent.
So
Okay,
this
that's
is
Converging. But this claim that
This
they're
is-
actually independent.
this is basically on this count sketch compressed vector.
so there are those, do you finally work with the tildes or the hats in the previous?
So finally we worked with tildes.
So the tildes already have gone through the discretization. I don't know if that goes around the objection that you have.
Where is the tilde?
So if you go back to the, yeah.
Yeah,
the thing is you look at,
yeah, the tildes are discretized, okay.
so there maybe the rational versus irrational you don't get to see at all.
Maybe. So what is
No,
the
but the thing is like, I mean, what do you say? So even if it, but how did the size of P enter at all? Because independence should just be a statement about discount sketch matrix, right? Because it has to hold for every P. So our P is also thought of as a random variable, and
So
then
P we can think of we are getting data matrix from some distribution which satisfies this property.
and the P, okay. P satisfied. Okay. But but the only condition on the norm of P is that there is moment constraint. Yeah, but this independence, I think,
Maybe I need to think on this like with my.
but is it that, so I mean like this equation 7 that, so that already is saying that it's converging to a product distribution.
Yes, yeah. So it's kind of easy
That-
application of this.
Okay, so when you say independent, it just means that they're converging to something. So
Yes.
they were never actually independent, they're getting
Converging.
closer and closer.
Yes,
Yeah, then
Okay, that's
So-
a different.
Which is what Jatin was saying.
Yeah.
Yeah, then
So yeah, convergence in this thing.
so convergence distribution to a product distribution.
Yes, yes.
Yeah. Okay.
That's the corollary of the.
Yeah, yeah. Then yeah, that's what. So because there is a corollary of the first one.
So
Yes.
yeah, so basically then we get the guarantee what we get in case of E2LSH. If case follows this and each entry of the input vector is small. This is what we get in E2LSH.
That's some small level.
Yeah. Okay, and we use this univariate Lyapunov central limit theorem and multivariate Lyapunov central limit theorem to prove our theorems. And the second contribution is how much time do I have? 20 minutes. Okay. So another contribution is using higher order count sketch. So higher order count sketch is kind of multimodal way, like kind of extension of count sketch. So suppose this is our data point and we can reshape it in form of a matrix or maybe a higher mode cube. So for example, in this case, suppose our input is a matrix. Here matrix is 1 point, not a set of points. Here matrix is 1 point. So we apply in higher order count sketch. Basically, we apply count sketch algorithm on each mode. Right. So suppose this is say D cross D matrix. Left side we'll apply K cross D and right side we apply K cross D transpose. Right. So we'll get K cross D matrix. Right. And it has been shown that the L2 norm or Frobenius norm of this matrix is gives unbiased estimation of Frobenius norm of original matrix. Right. So this is higher order count sketch proposed by Shi and Anand Kumar. So our second contribution is basically we replace, instead of using count sketch, we use higher order count. So count sketch is mathematically can be seen as, so suppose P is our input point and we compress it into K dimension, CSP1 to CSPK, and CSPL can be seen as summation Hi is equal to L, I from K, SIPL, where H is hash function maps index from D to K and SI as a sign function which maps index from +1 or -1 with probability half. In higher order count sketch, we multiply it with n sign functions, where n is the mode. So in case of matrix, you can think of n is 2, right? So we can multiply with two sign function, S1 and S2, and follow the same thing, right? So in that case, our hash function is, so suppose P is our input point, SCS of P will give us a tensor of size of mode n and dimension along each mode is k1 to kn. Right? So we reshape it and make it a vector. And suppose k is product of all these k's. Right? So we are again compressing d-dimensional vector to k-dimensional. And our hash function is same. Right? We scale it by root k plus b by w. Right? So this is our hash function. And so for CS2LSH, our time and space complexity is order D. For SCS2 of LSH, time complexity is order D, but we get again improvement in space complexity. Why? Because suppose our matrix is of size, input is of vector of size D. We can think of it as matrix of size root D cross root D. So to apply count sketch along each mode, we need two matrix which has non-zero entries root D. So instead of space complexity D, we are using 2 into root D. Right? So if we reshape our data point into mode n, we'll get space complexity d raised to power 1 over n into n.
So just want to, so n is going to be when you take the vector and reshape it into a tensor, how many dimensions you have?
So suppose
Order of the tensor.
if we
The order of the tensor.
order of tensor. Suppose
Okay.
we reshape it into matrix n is
Then
2. We
N is
reshape
2 and the side lengths are going to be square root is like if
square-
you're, yeah, of course.
square
I see.
root D.
Okay.
So it is 2 root D instead of D.
And the same CLT statement holds about this another problem.
Not same, like there are different variant of central limit theory. So again, we need to show that each element of HCSP follows asymptotic univariate normal distribution and they are independent. And we use it we prove it under these conditions. So they may look weird, but roughly they are saying that each coordinates are small, and like you can think of k is small o of d power something, d power 1/3 for simplicity. And then we show that entries follow multivariate normal distribution and they are independent in concurrence. So for proving univariate normal distribution, we use CLT of sum of bounded random variable central limit theorem, which is already known. So basically, the central limit theorem is, suppose y1 to yd is a family of bounded random variables such that each yi is at most d. And suppose we generate sigma d is a dependency graph and m is the maximum degree of sigma d. Then we define SD as like this sum of all variables and sigma d square is sum of all variables. Then if this condition holds true, then this will hold. So we use this central limit theorem. But for multivariate thing, there was no such thing known. And we proved it along the same lines. Like, so if y1 to yn is a family of r-dimensional random bounded random variables such that each L2 norm of each yi is at most a, and si is sd is sum of all yi's, and sigma d is covariance of sd. Then if this condition holds true, then SD follows multivariate normal distribution. So this is what we proved like during the course of proving this multivariate normal distribution. Right. And now I'll show some experiments to show usefulness of our result. Right. So we used the dataset that we use has small to kind of large dimension, and the points are also small to large. And we use two metrics. One is indexing time, and indexing time basically the time required to create our hash table. And the second thing we also, so far in the proof we have not seen how good our, like if we use this hash function, how good the kind of indexing quality will be, right? So we also need to measure it. So that shows us the trade-off between recall and query time, right? So the first plot is basically we take our data set, compress it into different hash code size. So here I'm using this notation M, but in the paper, rest of the paper, we used it as K. So these are the different hash code size, and we noted down the time required to compress our input points into this hash code size. And CS E2LSH is the standard index mode 1 hashing algorithm. And CS E2LSH is the standard index mode 1 LSH algorithm. CS E2LSH is our proposal. And SCS E2LSH for n equal to 2 and 3 is basically when we reshape our data in form of matrix or cube. Right? So we can see that for all these data sets, CS E2LSH, the time required to compress or create a hash code grows linearly with the hash code size. But in our case, it is kind of constant, right, across all data sets.
The higher order didn't really help.
Higher order help in saving space complexity. But for indexing, it basically doesn't help, even
It worsens.
it worsens. So it majorly saves in space complexity. Then we also measure.
Why do you not have any increase at all? As you, I mean, is the number of non-zero entries is increasing in the matrix.
But still, it is kind of very close to zero. It's not zero, but higher than zero.
Yeah. So there should be some slope.
It's slow, but it is. If we see, if you put this in along with this plot,
No, but the last one is what I know, because the last one looks like if there is a or there's an intercept.
Okay, so if you use count sketch, irrespective of on which dimension you are compressing, the time running time will be same, right? So in count sketch, basically it will be order D only.
Order D, right?
D. So it will D is same, right? So D or NG of P will be same. So that's why it's kind of straight line.
Total sparsity.
Whereas this also depends on hash code size. It's order K2. So, and we use this recall measure. So in to see how good our hashing algorithm is to measure approximate nearest neighbor search. So what we did, we split our data set into two parts, 90% and 10%. We use 90% to data points to use for creating hash tables, and the remaining 10% we use them as query vectors. Okay. So for every data point, we noted down their actual closest nearest neighbor, their ground truth closest 50 nearest neighbor. Suppose that set is S, and then we noted down S prime, which is the estimation using our various baseline algorithms. Then we report recall, which is size of S intersection S prime by size of S. Right? So it captures how many actual nearest neighbor our algorithm is actually able to capture. Right? And higher recall is better. Right? So, and the x-axis corresponding to the time to find those S prime, as well as S prime. Right? So we can see that it is, so basically the best that we can achieve for is E2LSH, right? Because that is baseline, standard baseline. We can see that for almost all baselines, all data sets, our algorithm is kind of comparable to E2LSH. It's kind of overlapping with green line, which is E2LSH. For GIST, it is CS2LSH is matching, but for HCS2LSH is slightly deteriorating because GIST dimension is small, so it's few hundred dimension only. But CS2LSH is also matching, right? So irrespective of dimension, we can use our algorithm, and whatever we recall we get on using E2LSH, we can get roughly using our CS2LSH. And then we also measure it by on x-axis trying out different values of that. It's basically the number of hash tables that we need to generate, the repetition step. And again, on y-axis is recall. And again, we can see that our algorithm is kind of comparable to E2LSH, right? Yeah, so. And so, yes, E2LSH is kind of very classical algorithm for locality sensitive hashing for Euclidean distance. There are various improved variants of it, which are proposed, which gives theoretical guarantee as well as heuristic, which works very well in real life data set. But in some way, they are using some variants of random projection. So potentially, whatever we are proposing here is just replacing this dense GR matrix by sparse countscape matrix can work here. It can work. It may give good result empirically. Proving theoretically may require some effort. So our techniques can be potentially extended to these improved variant of LSH. And LSH has been used extensively in many real life applications like finding faster near duplicate detection, audio similarity identification, acceleration, model compression, and so on. So potentially in those cases, we can use our algorithm to get improvements. I'll just take 2 minutes and then I'll wind up.
You have 7 minutes, you can't stop early.
Okay. So there is another LSH proposed by Charikar, which is LSH for cosine similarity. So the algorithm is, so basically it is LSH for cosine similarity. Input point is P and Q, and the cosine similarity is inner product of P and Q by their L2 norm. So the hashing algorithm is this. We generate a random vector R whose each coordinate is from normal distribution with mean zero and unit variance. And the hash code is basically take inner product of P with R. P is our data point and R is the random vector. And based on the sign of this inner product, we assign hash code either 1 or 0. Right? And they showed that the probability of hash value is same is monotonic to the angular distance. Right? And this can also be seen as, suppose if you want to generate k-size hash code, this can also be seen as like matrix vector multiplication. Like, so this is our input vector. We generate a random matrix of size k cross b. Each entries are from Gaussian. We get sketch vector, and then we take sign of each component based on their inner product. Right? So again, it is in the same line of E2LSH, inner product plus discretization. So we also applied, again, time and space complexity is order KD. Our contribution is replacing this E2LSH, replacing this dense projection matrix in SRP by sparse count sketch matrix, and we get similar improvements. We showed two improvement in CS, two classical locality sensitive hashing algorithm. One is E2LSH for Euclidean distance, and second one is signed random projection for cosine similarity. So, and we get the same kind of improvement. So yeah, so these two are our work, which gives improvement in time and space.
The first one is matching, it's not just the, right?
This,
CSSRP versus.
so this one is matching. Here we get improvement in space complexity. So this is our earlier work.
Okay.
And so this is matching, but we get improvement in space complexity when we use higher order count sketch. Yeah, that's all I did. Thank you for your time.
Questions?
So essentially wondering, so this thing of doing a random projection, I mean, there are situations where, I mean, normally we would, I mean, the ideal situation would have been to take this, I don't know, A cross D matrix, I don't know which is capability, but whatever, you take that matrix and every entry of this matrix is going to be some, I don't know, uniform Gaussian or something like that. Is there a way to, I mean, count sketch is one way of doing this. Like, basically, I'm trying to see, can I introduce dependencies in the matrix and still expect the same sort of performance? There are like some situations where you can replace such a matrix with a Toeplitz matrix or something.
Yes, you can use, so there are various variants of it, like you can use fast gel transform. So instead of, so in that case, this projection matrix is kind of product of three matrices. One is sampling matrix, another one is Hadamard matrix, and third one is random diagonal matrix. So,
okay.
So fast gel transform, we call it as fast gel transform. Instead of, in that case, the running time is, here the running time is KD. They're using this like Hadamard transform, we can get it in D log.
So that's what I was going to go for. I was basically saying that there are some specific matrices such that matrix vector product can be done very efficiently. So I was wondering if any of those are.
Hadamard, that is it.
Okay.
And you can use also this circulant matrix and Toeplitz matrix. Those are also being explored.
Can you just go to the last table that you showed? Like, can you say anything about lower bounds for these? Are there?
If you looked at bounds, we have not
Okay.
explored in the bound.
So there's a sparse list of kind of, but there we are log n log the number of points dependence is that why?
Yes, so the number of non-zero should be log n, I think, in each column.
Yeah. So that's why you don't want to use.
Yes.
So this one,
What's the sparse J guarantee?
So
the sparse guarantee is that if you have login points, then all the inner products are all the.
Oh, they're faithfully mapped.
Yes, but yes, yeah. But the thing is that like it's a log-n dimension. So you're going from D dimensions to log D dimension. But then you also expect that there are not that many points. The points are about polygon D. That's it. So that's why you don't want to use. And there has to be too strong a guarantee that all the inner products.
basically, in terms of if you want to focus on the time complexity, count sketch gives us the best. It is energy of input point.
More questions? Yeah, it's time to.
So you know the way to read that dog. Yeah. The dog that keeps doing. Yeah.